Hi folks, today we're going to put things in perspective. And I mean that literally. We're going to take our objects and we're going to make them smaller or larger based on how far they are from this notion of an eye. So we're going to have this field of view, and we're going to introduce this notion of what we'll call an image plane. This will be kind of like a film that will collect the light that passes through it. And when we've got an object, say this little tree out here, and let's say the top of the tree, there's going to be light rays that come from this top of the tree to the eye, and we want to know exactly where they land on this image plane. This image plane then will map to our viewport. We'll do that for every sort of object, every vertex position that we have out here, and we'll end up with the things that are closer to this image plane, like this tree, will appear with a bigger footprint than the things in back, even if they're the same size. So here's another tree. It's got the same height in this space that they're defined in, but when we project it, well, it lands not as tall as its neighbor up in front. So that's kind of the idea behind perspective, is that the size of something is dependent on its distance from the eye. So we'll end up scaling our objects basically based on how far they are from the eye. Okay, we're going to have to develop a slightly more rigorous definition of the mathematics behind it, and it'll get a little involved today, but it's kind of an interesting story of how it all happens. So let's go ahead and draw this again. Reminder, what we're doing here, we're doing a projection transformation. That's something we're defining. We've already defined one, and that's the orthographic projection. In that situation, things that are farther back appear the exact same size as the things that are closer. But we want to do that slightly differently, and so we're going to need to do two things. First, we're going to need to project our vertices onto that image plane, on plane, and then we're going to have to do what all projection matrices have to do, and that's map that plane to that -1, 1 space that OpenGL expects. So the thing you write to GL position ultimately is going to fall into this -1, 1 space. And I think that's pretty much it. It'll be a little bit of a circuitous route to get there, but we'll end up doing it by the end of this video. Alright, let's look at that picture of the tree again. Here's our tree. It's a little lopsided. And we have to introduce this notion of an eye. That's just for perspective to have any meaning, we have to have an eye. We're also going to throw in this image plane. This is kind of like the film that will be collecting the light that passes through it. And so we will focus on this point right here. This point, we will call it X, Y, and Z. This is something that comes in as a vertex attribute. It's known. This will be the eye back here. For most of the math here, it'll make more sense. It'll be less complicated if we assume the eye is at the origin, and everything is defined in terms of the eye being at the origin. So technically these X, Y, and Z, this won't necessarily be object space coordinates. We might have to move them around and rename them, make them relative to the eye. So I'm going to do subscripts of E there. When we write a camera class, we'll write it such that it puts the eye at the origin. And then we'll also, the user will need to specify what this image plane, what it looks like, where it appears. And we will do that through a few values here. We'll ask the user for a field of view on the y-axis that will produce this angle right here. We're also going to ask it for an aspect ratio, which we get from the window, the width to height ratio. That'll determine our field of view on the x-axis. It'll just be based on our field of view on the y-axis. The other thing we need is this value right here. This will be n, and that's the distance to this image plane. Most graphics APIs have n greater than 0, the ones that I'm familiar with. So this will be a positive distance, and I make this qualification because most graphics APIs I know also kind of assume that the eye is looking down the negative z-axis. That's the convention, that's the standard, and what I mean by this is that for something to be visible here on our screen, its z coordinates are going to be negative. All right. You might question that standard, and I do. In fact, I fought it for several years in my own code, and it's not worth it because all the tools assume that negative z is where we're looking down. Okay, so, but when we specify n here, it will be positive. It'll be a length of that triangle. And what we would like to know here is, where does this point on the top of the tree, where does it land on this projection plane? This is the projection plane that will ultimately map to our viewport. So what is this point? Let's just look at the y value, the y component of it. Let's call it yp. And what is yp? Well, yp, if you go back to your high school geometry classes, you'll be able to find it by imposing sort of these triangles here. We've got a small triangle embedded inside a larger similar triangle, and we can relate these two triangles to each other and find out our yp. If you'd like to figure it out yourself, pause the video, but we'll keep going. Yp, this is that length right here of this triangle. It is to that width, n, as, well, what's this? What's the corresponding height over here? That's ye. And what's this corresponding width of the big triangle? Well, that's our distance from the camera, ze. And that's it. One thing I guess we should note here, we said ze is negative right here. That's just by definition, but we also said that n is expressed in a positive form. So this one's negative, this one's not. We should probably fix that so they both have the same sign. And we can solve for yp now. Negative n times ye over ze. Okay. Now we can do the same for x, and we end up getting a very similar expression. Let's just rewrite them here. xp is negative n xe over ze. And yp is negative n ye over ze. That gives us this point right here on our image plane. Let's say it maps right there. So this is xp, yp. Here's the center. This is what the focal point that the eye is looking at. And now we have this point on the projection plane, but now I said the next step we have to do is turn this projection plane into those normalized device coordinates. So somehow we have to turn this xp and yp into sort of proportions of the image plane. So how much up is yp in our little image plane? And the only way we can figure that out is if we know the top value here, let's call it top, and the right value here. If we do know those, then we could get those normalized coordinates. We could say xn is our normalized x coordinate between negative 1 and 1 is just xp over r, that's the proportion, and yn is yp over t. So these would give us the proportions, and then we'd be able to do our transformation. We'd have our projection into that normalized space just like we need. Well, how do we figure out t and r? Well, we can do it. We said that this angle right here, fovi, we have, and we also have n as the distance to this image plane. So half this angle is fovi over 2, and this height right here is t. That's how tall the image plane is above the focal point. Well, this is just the tangent problem. So we could just do tangent of fovi over 2 as what's the opposite length? That's t. And what's the adjacent length? That's n. So t is just n times tangent fovi over 2. Okay, so we could then, we now have a full transform that would get us our normalized x coordinate. And right can be achieved at similarly, well, we don't have to go to quite such lengths. We remember that width over height, that's our aspect ratio that relates our window's width to our window's height. Well, we want the image plane to be in the same proportion, otherwise we're just going to get stretching when we map the image plane to the viewport. We want them to be consistent. So we can relate r to t in the same way and force this proportion to be equal, and we can solve for r. R is just multiply both sides by t. We've got t times the aspect ratio. All right. Hey, so now we can figure out, using combining these equations and these. Whoa, let's fix that. All right, these two up here, we can develop a full expression to turn our I space position into normalized device coordinates, that -1, 1 space. So let's rewrite those. Xn is -n over r times xe over ze. And then yn is -n over t times ye over ze. Okay. Now, every time we've had a problem like this in the past, we've gone to matrix multiplication. We've tried to figure out how can we use matrices to make this happen quickly on the graphics card. And so you might start thinking about that and draw out your matrices and figure out, okay, how can I make this work? Our vector that we're transforming it's xe, ye, ze, and 1 is the homogeneous coordinate. We're going to multiply that by something, and we want to get out xn, yn, and then we'll come back to this one and the other two values too. But we definitely want xn and yn. Those will get us our pixel coordinate ultimately when we do the viewport transform. So how can you, relying on the mechanics of dot products, how can you get xn out of this? What could this row be such that it produces this quantity? And it's not going to happen. You could try to twist it and bend it and squeeze it however you like. Dot products will not end up with a xe over ze. It's just not going to happen. So we have to resort to a little trick. We're going to do something here. You see this negative sign and you see this ze. Well, that's in both of these. And we're going to do a little sleight of hand here. We're going to multiply both sides by -ze. And we're going to get -ze xn as no negative anymore. We just removed it. N over r times xe. A much tamer equation that looks like a dot product might fall out. And same over here. -ze times yn is, nope, no negative sign again. We took it out. N over t times ye. Alright, well, we can do dot products with these. These are just scales. So this nr, that's just a scale factor. N and r are both derivable values. So n over r, if we dot this row with this vector, how do we get this? Well, there's no ye, ze, or homogeneous component here, so zero everything else out. And when we do that dot product, we will get this as our value. So instead of just plain old xn, we get -ze times xn. A little more than we want, but it's something. And good news is going to fall out here in a bit. But okay, same for this one. How can we get this result? We scale y and zero everything else out, and we'll get -ze over yn. Okay, so what have we gained? We've gotten close. We need to get rid of these -ze's in order to get our normalized coordinates so that the viewport transform can turn these into pixel coordinates. And the good folks that thought long and hard about this problem thought, well, here, yeah, this is tricky. Let's do a little trick. After you get a vector of this form, we are going to, you don't have to do it explicitly, we'll do it because we're the graphics API writers. We will take your homogeneous coordinate that you put right here, we will multiply your vector by 1 over that homogeneous coordinate. We'll divide by w, basically. And that will be this little special trick that we'll offer you. And if we can just get the right homogeneous coordinate in here, we can end up with the values we really want. And so we really want xn, yn, and something, and 1 at the end. And so what does w need to be? It needs to be -ze. So So when we do that it's called the perspective divide. When we do that perspective divide, these negative ZE's will go away and we'll get those normalized coordinates, just like we want. Okay, so how do we get a negative ZE in this bottom component, this homogeneous component? Well, that relies on this row of this matrix dotted with this. There's no XE component, no YE component, 0, 0. There is a ZE component, but it's negative, so we need a negative 1 there, and there's no homogeneous constant offset there. So 0. And that, my friends, gets us a good part of the way to a perspective matrix transformation. This is not resolved yet. Let's save that for a moment, and let's go implement what we have in code. We've done a fair bit of talking, so let's go see. We're going to make a new matrix creator. It'll be a perspective transform getter, and we will take in just those values that I expressed earlier. So we'll have a float for our field of vision on the y-axis, a float for our aspect ratio. This is going to define the image plane, float for our near value, and as we'll see in a bit, we'll also need a float for our far. We'll have something called a clipping plane. Anything that appears less than n, closer to the camera than n, will be clipped out. Anything that appears farther than f will get clipped out. Okay, those 4 values alone should define our viewing frustum, the space that we see. And now let's go implement. Okay. Ultimately, we're going to need a matrix. We'll call it M, and let's start it off with the identity to get zeros in all the right spots. And our matrix looks like this. We saw it down, most of the components down here. So we need our N, which we have. We need to figure out R and T. We did that on a slide back or so, and we said that T was the tangent of the field of view divided by 2. But we need this to be, probably field of view will be in degrees, and we can turn that into radians, like so. And we need to multiply all this by the near value. We saw, oh, let's close that. The near value times tangent, right there. You can scroll back if you don't remember why we did that. And R is the aspect ratio times T. Now, we've got enough to fill in many of the components of our matrix. We've got N, R, T, and -1, well, that's constant. So M00, 0. That's just R over T. No. N over R. Don't trust me. And then N over T as the 1, 1 component that scales the Y. Let's leave the middle row blank for now. Let's 0 it out. And then the 3, 3 component doesn't have anything in it. That diagonal's wiped. The one before it, though, that's where we get the -1, 1. So that is column 2. That'll have -1 in it. Okay, so that's a good start to our matrix. Row 2 is to do. We'll come back to that. And let's go ahead and quit this. I've got our perspective test here. Here's a cylinder. It's not currently in perspective yet. It's using an orthographic projection. Let's go change that. We'll find the projection and replace it with something that's in perspective. So matrix 4, get perspective. Here's where we get to fiddle and play with values. You could think about what the best field of vision might be. I don't know what it is on a human, but I'm going to guess 45. I think that's a little large. And then we have to specify the aspect ratio. Well, that's just whatever the width to height is of our window. We can grab that with a getter. And then our near and far clipping planes. We can just go ahead. These need to be positive values. We can just pick random numbers for now that we know our objects will fall within. Okay, let's go ahead and give this a compile and see if anything is working. And is it? It's really hard to tell. That doesn't look great, does it? But if you look around, it seems that we're inside the cylinder. Why is that? Well, right now our object space, the cylinder was defined around the origin. Well, the camera's at the origin, the eye's at the origin, so they're in the same spot, and that's why we're inside of it. And that stuff's just a little too close to make sense out of. So what we're going to do here is I've got a matrix here called push, which basically pushes the object away from the center. So we push that down the z-axis 3 units to get away from the camera. And let's have a look at our shader. Nothing different happens inside our shader than what we had before with an orthographic projection. So right now, yes, we have a different kind of projection matrix here in projection. It will produce a homogeneous coordinate in our GL position that is not 1, but we don't do the perspective divide. OpenGL will do it. It actually does the clipping operation where it says, hey, this geometry is not on my scene, it's off screen. It'll do the clipping before the perspective divide. So it's slightly cheaper to do it that way, but that's why we don't do the perspective divide, because it does the clipping for us. And nothing changes from our perspective, no pun intended there, in the vertex shader. Alright, let's go recompile. And how's that look on your end? It looks terrible on my end. We've got something left to resolve. So what happens right now is that our geometry is really just, it's getting flattened into a plane. Because while we've got the X and Y positions correctly on the viewport, we don't have the depth figured out. So we've basically zeroed the ZE coordinate on all incoming attributes. And so when the depth test comes along, it says, well, they're all 0. They're all to be drawn, basically. And so we need to fix that. We need to give that third component of our vector, the one we left unresolved, not a 0 value, but some value that helps us sort according to the depth test. Alright, and this one is probably the more complicated part of the perspective transformation. We need to figure out this row so that we can get a good value here when we do our dot product. Alright, let's clean this slide and just focus on that row. We're going to have some row 2 here when we dot it with XE, YE, ZE1. We want to produce some good sortable depth value. Well, we know that when we've got, here's the near, here's the far, it's technically negative near and negative far. We want basically to map these depths to a good set of range 2, just like we did with the X and Y. And so we really want negative n to map to negative 1 for a depth value, and negative f to map to positive 1 for a depth value. That's the OpenGL way. I think Direct 3D uses 0 and 1 instead of negative 1 and 1, but it doesn't matter. We can do this. And so we need somehow to figure out how can we map values in this range to values in this range. The first observation we can make is that the depth value we give doesn't really depend on, say, the vertical position of our point. That doesn't matter. All these YEs will map to the same depth. It doesn't matter. So we can say that YE has no bearing. Let's zero it out so that when the dot product happens, it's not included. Same with XE. So we can definitely figure these two out. This will zero out these components. And now, what do we multiply by ZE? I don't know yet. Let's leave that as a variable. And what do we multiply by the 1? I don't know yet. Let's leave that as a variable. Okay. Has that bought us anything? Yeah, it actually has. If we multiply out the dot product, so we can do A ZE plus B times 1. That's the dot product operation, and then we do the perspective divide. So divide by ZE negative. When that ZE is negative n, this is the case, we want this whole expression to evaluate to negative 1. So we could say when this expression, when ZE is negative n, so when negative n a, right here, just rewritten, plus b over negative n, so positive n. When we have that, we want to evaluate to negative 1. And when we have ZE equals negative f, in this case, we want that whole expression to evaluate to 1. So writing this again, negative f a plus b. When we divide that by negative f, or f, we get 1. Okay, well, are we any farther along? It turns out we are. We now have two simultaneous equations that we could solve one of them for b and drop that definition of b into the other and solve for a. So let's start with this one. We could turn this, we could multiply both sides by n, and so that would give us an n on the right side, a negative n, right there. And then we could add na to both sides, and that would yield us just a b on the left and an na on the right. Okay, so that's our definition of b, negative n plus na. Now, going back over here, let's do negative f times a plus, and then here's the definition of b, we can swap in negative n plus na all over f gives us 1 from the right hand side here. Okay, let's simplify this. We've got, if we multiply both sides by f, we'll have f on the right hand side. And what else do we have stray here? We've got a negative n right here. Let's add n to both sides. So that's been taken care of. Let's add n to both sides. That will throw that on there. And we will have left two terms, both with an a coefficient. So let's factor that out here. And we will have negative f plus n left over to be factored out here. Okay, let's solve for a. A is simply f plus n over negative f plus n. And you'll often see this written, people will factor out a negative 1 from here, and so they'll write it instead as negative f plus n. So the negative 1 is factored out of the denominator. The signs flip, so this will be a positive f, and this will be a negative n. So, and the way I think about this is that perspective is fun. That kind of looks like fun. Okay, so negative f plus n over f minus n. Let's take a break now and go write this in. This will be our a component, which is row 2, column 2 of our matrix. And not there. So row 2, column 2 will be negative f plus n over f minus n. Alright, we still have one more component, and that's that row 2, column 3 component. This will be b. And let's go solve for that. Okay, here's our definition of b. So we said that was what it is here. We now have a definition of a, so we can figure this out. Let's go make some more room here. Negative n plus n times, well, here's a. It's a negative f plus n over f minus n. And we can factor out that one of these negative n's and simplify this a little bit. So here's negative n, and we'll have left over this term, multiply by 1, and this term multiply by f plus n over f minus n. And let's make this 1, let's turn it into an f minus n over f minus n, so we can combine these fractions. Negative n, and we'll have f minus n over f minus n plus f plus n over f minus n. Okay, and that yields these f's. These will combine, but we'll have two f's. These n's will cancel. So we will have negative n and two f's multiplied by each other when these all get multiplied through. And that will all be over f minus n. And that, my friends, is a perspective matrix. Whew! Try thinking of that on a deserted island. I don't know. Okay, let's go fill out our last value. Negative 2.0 times far times near all over far minus near. Whew! Let's go try it. Let's see if our depth works now. I can back it out. I just use the plus and minus keys to add more push to my matrix there, and it definitely is in perspective. If I look at it from the ends and do wireframe mode, my caps are not the same size. The farther one appears smaller. It has a smaller footprint on my viewport. Nice. And there's Suzanne. Let's go back to fill. Filled mode. And she is also in perspective. Everything's in perspective. You can see her. There's some what's called foreshortening going on here. And here's my donut. The backside is smaller than the front. And it looks much more realistic. Let's close it here. I'll also bring up the terrain. And there's our terrain. And so now we can start to see things just as the human eye sees. And that's pretty fun. Okay, well there's perspective. Maybe you didn't want to go into it that deeply, but it's hard to write a good piece of graphics code without getting some perspective in there. And now you can hopefully see kind of how people arrived at it. Okay, we'll see you next time.